Welcome to the deep dive. Today we're looking at something, well, pretty exciting AI that can actually talk back to you, like in real time.
Yeah, it feels like a big step.
Imagine just chatting with your assistant, and it keeps up, no awkward pauses.
Exactly. We've been digging into this great article from MarkTech Post that just came out yesterday, May 6th, 2025. It covers some really groundbreaking stuff from researchers over at the Institute of Computing Technology, Chinese Academy of Sciences.
Okay.
They've developed this new family of models, speech-capable LLMs, called LLaMA Omni2.
LLaMA, Omni2. Sounds comprehensive, like you said. The article mentions this is way beyond the older systems. What was the holdup before? Why weren't they real time?
Well, the older way involved what they call cascaded systems.
Cascaded.
Yeah, think of it like a production line, separate steps. One AI understands the speech, passes it on, another one figures out the response, passes that on, and then a final one speaks it.
Ah, okay. Like a relay race.
Exactly. And each handoff, adds a delay. It slows things down.
Yeah.
What LLaMA Omni 2 does is more of an end-to-end approach. It's much more integrated,
So faster.
much faster. It cuts down those delays significantly, like one super athlete doing it all.
Okay, let's get into that integrated approach then. It's built on the Qwen 2.5 Instruct series, the article says.
That's right. Qwen 2.5 Instruct provides the core language model foundation, and LLaMA 2 comes in different sizes, from 500 million up to 14 billion parameters.
Parameters being like the brain power, roughly.
Sort of, yeah.
Yeah.
The capacity for knowledge and reasoning. And inside LLaMA 2, it's got these different, specialized modules working together.
Okay, like tools in a toolbox. What are the main ones?
So first up, you've got the speech encoder. It uses a model called Whisper Large V3.
Okay, Whisper. I've heard of that.
Yeah, it's well known. Its job is basically to listen to you speak and break that down into what they call acoustic tokens.
Acoustic tokens, like
Yeah.
the fundamental sounds.
Pretty much, yeah. The smallest bits of sound the AI needs to recognize.
Got it. So sound becomes these tokens. Then what?
Then comes the speech adapter. It takes those tokens, does a bit of downsampling, sort of compresses the data a bit to make it easier to handle. And then it uses a feed-forward network to kind of translate these sound tokens into a language the main LLM can work with.
Bridging the gap between sound and the brain, essentially.
Exactly. And that brain, the core LLM, and that's the Qwen 2.5 model we mentioned,
Yeah.
it does the actual thinking, figuring out the response.
Right. So it thinks in text, basically.
Well, it processes the information derived from the speech. And then to get that response back out as speech, that's the job of the streaming TTS decoder. TTS meaning text-to-speech.
Streaming TTS. That streaming bit sounds important for the real-time feel.
It's crucial. This part takes the LLM's text output and first turns that into speech tokens using an autoregressive transformer.
Okay.
Then, to actually create the sound waves, it generates a Mel sectogram. Think of it like a visual map of the sound. It uses a model based on something called Cozy Voice 2.
Cozy Voice 2.
Yeah, and the technique, this causal flow matching, is really good at generating the audio piece by piece, like as the text comes in. That's key for the low delay of the streaming.
Wow. Okay. Lots of complex parts working in sync.
Yeah.
The article also mentioned a gating mechanism. What's that about?
Ah, yes. That's a really smart piece. It basically blends the LLM's internal understanding, its hidden states, with the text representation before synthesis.
So it helps the voice sound more knowing, contextual.
They found if they took it out, the speech quality dropped quite a bit. It ensures the AI's thoughts align properly with the words it's actually speaking, more coherent.
Makes sense, like speaking with intention. Okay, let's talk about that real-time speed, this read-write strategy for streaming. How does that actually work?
So the read-write thing is how they manage the flow. For every, say, R text tokens the LLM thinks of,
Okay.
the system generates W speech tokens at the same time. They're working in parallel.
Reading text while writing speech.
Precisely. And they found the sweet spot
But
experimentally.
what was that ratio?
The best results came with R3 and W10. So for every 3 text tokens, it generates 10 speech tokens.
And the result is that low latency.
Yeah, it gets the latency down to roughly 583 milliseconds.
Wow. Under 600 milliseconds. That's barely a noticeable pause in conversation.
It's getting really close to natural turn-taking time.
The article also threw out some scores, ASR-WER and UTMS. What do they tell us?
Right. ASR is word error rate for speech recognition, basically.
Yeah.
How well the system understood the speech it heard internally. 3.26 is a low error rate, so pretty accurate.
Good understanding. And UTMOS.
UTMOS is about the output quality, how natural the generated speech sounds to humans. A score of 4.19 on a scale probably up to 5 is quite high. It means people thought it sounded very natural.
So it understands well and speaks naturally. Impressive. Now, usually tech like this needs massive training data, right? But it says here just 200,000 dialogue samples? That sounds small.
It does seem surprisingly efficient, doesn't it? And this is one of the really clever parts. They didn't just collect endless hours of people talking.
No, how then?
They synthesized it. They took existing text data sets, instruction-following ones like Alpaca, UltraChat, and used other AI voices, Fish Speech and Cozy Voice 2, to turn them into spoken dialogues.
Ah, so they generated their own speech training data from text.
Exactly. Using diverse input voices, but keeping the output voice consistent. It's a really smart way to bypass the need for huge, manually collected speech corpora.
That could be huge for training these models more easily.
It really could. It might lower the barrier for developing these kinds of systems, maybe for less common languages too.
And the training itself happened in stages.
Yeah, 2 stages. First, they optimized the speech-to-text part and the text-to-speech part kind of separately.
Okay.
Then, in stage 2, they fine-tuned the whole end-to-end path together, including that gating mechanism and the decoder, sort of optimizing the whole flow once the parts were working well.
Makes sense. They also found that multi-turn dialogues were better for training than single questions and answers.
Yes, definitely. Training on back-and-forth conversations helped the model learn the flow and context of real interaction much better than just isolated Q&A pairs.
Like learning conversation by actually conversing.
Pretty much. It makes intuitive sense, right? Real chats aren't just single shots.
And that 200,000 sample figure, was that like the magic number?
Apparently, yeah.
Yeah.
They noted that performance seemed to plateau around there. Adding more data didn't give them significantly better results, suggesting they hit a point of high efficiency.
Very efficient. So how does LLaMA Omni2 stack up against the competition? The benchmarks looked interesting.
They did. They tested it on things like answering spoken questions, following instructions given verbally, and a key comparison was their 7B model, 7 billion parameters against GLM4 voice, which is a 9B model.
Okay.
The LLaMA Omni2 7B hit that latency we mentioned, around 583 milliseconds. GLM4 voice, over 1,500 milliseconds.
Whoa, nearly 3 times slower. That's a huge difference in feel.
It's a night and day difference for interaction, absolutely. And what's more, their bigger 14B LLaMA Omni2 model actually outperformed the baseline models, even though it was trained on much less speech data than some competitors like GLM4 voice.
So better architecture and training trumped just having more raw speech data in that case.
It certainly looks that way. It highlights how effective their specific design and training strategy are.
And within the LLaMA Omni2 family, bigger was generally better.
Yes. The results showed performance scaling with model size, generally. The 14B was better than the 7B, which is better than the smaller ones. That's pretty typical.
So pulling it all together, what's the main headline here, the big takeaway from LLaMA Omni2?
I think the core message is that really high-quality, super low-latency spoken conversations with LLMs are possible without needing those absolutely enormous speech data sets that were typical before.
Right.
Their modular design, the clever training with synthetic data, the streaming synthesis, it all adds up to a practical way forward for real-time speech AI.
It solves that frustrating lag we've all experienced with voice assistants.
Exactly. It makes the interaction feel much more, well, human, fluid.
It really does seem like it could change how we use AI assistants fundamentally. More like partners, less like tools you issue commands to. Where else could this real-time speech make a big difference soon?
Oh, loads of places. Think about customer service bots, much less frustrating if they respond instantly.
Definitely.
Accessibility tools are a huge one. Real-time translation could become incredibly smooth. Education, collaborative tools where you brainstorm with an AI.
Yeah, you could really see that. Having a proper spoken dialogue opens up so many possibilities.
It really does. The potential is massive once that interaction barrier drops.
Okay, so quick recap. LLaMA Omni2, big leap in real-time spoken dialogue thanks to smart architecture, efficient training, streaming tech.
That sums it up nicely. They've shown a really promising path forward. Clever design can really make a difference.
And if you listening want to get into the nitty-gritty, where can people find the details?
Yeah, the MarTech Post piece mentioned the researchers are releasing the paper, the actual models, and the code. Look for them on places like Hugging Face and GitHub.
Excellent. So the resources are out there for anyone who wants to dive deeper or even build on this. All right, so as we wrap up this deep dive, here's something to chew on. How is this kind of truly real-time, natural, spoken interaction going to change how we relate to technology every day?
Yeah.
What new things become possible that we haven't even thought of yet when talking to AI is as easy as talking to a person? It's definitely an exciting space to watch. Thanks for joining us on the Deep Dive.